right, so in section 3.1 we talked about whole numbers and addition and subtraction. And then in 3.2 we talked about algorithms for addition and subtraction, that is ways of doing the addition and subtraction. 3.3 that I was non-part of for, but on 3.3 we talked about kind of the concepts behind multiplication and division, right, the different models and whatnot. And then in 3.4 today we're talking about algorithms for multiplying and dividing. All right? So to start with, I'm actually going to bring up a concept that seems a little bit oddly placed in here, but it's there for a good reason. And it's the idea of exponents. So you've seen exponents before, and you have also, we talked about in the last section, multiplication, or 2 sections ago, multiplication is really just repeated addition, right? If you had to add the same number together a bunch of times, a shorthand way of doing that is multiplying, right? I don't want to add 5 plus 5 plus 5 plus 5. No, I don't want to do that. I want to multiply because it shortens the method. And exponents do the same thing, okay? So exponents are a shorthand way of multiplying. So if I multiply the same number together a bunch of times, I'll use exponents instead because it's a shorthand method for doing so. So if we've got 8 at the end here, this is just a multiplied by itself n times. And this actually works for a rational number a. Right now in your book we're doing it for whole numbers, but I went ahead and put natural and rational numbers in here because it actually works for all rational numbers. And when you guys get to Math 2 with me next semester, those of you who will be coming on along, we'll do rational numbers in Math 2. I know, it's exciting. So, all right, so the first thing I want to show you is the properties of exponents that apply to whole numbers. Okay, so this is an abbreviated list of properties. This because we're only doing whole numbers. So, do you guys remember what happens when you have 2 values of the same base that are multiplied together? Do you know what you do? You add what? Exponents. Okay, you add the exponents. I'm going to show you the line for it in a minute, but you do add the exponents. That is the correct method. Now, 1 and 2 are very similar because on number 1, we've got them multiplied, and on number 2, we have them divided. So if multiplication turns into addition of exponents, then division will turn into subtractions, right? Again, I promise to give you a concrete example in a moment. How is 3 different than 1?
It's raised to another power.
As opposed to what, Lauren?
Multiplied. Just like from being the same power and multiplied into now a power above him.
Okay, and them being the same power.
The same base.
Same base, right? In fact, what I don't have on number 3 as opposed to number 1, I don't have the base written twice. There's also a set of a red flag, right? So one issue is the parentheses, the power, the power. The other issue is that on one of them I actually have the base written down twice. And so this is the one where you multiply the exponents, okay? And on number 4, it's not a variation of 3. Beth, you have an agent? What do you think? A to the m, maybe, is that what you mean? Yeah. And then b to the m. Now, this is different than the one we just did on the board over here, right? What's different? That's addition, that's right, Emily. I had addition on that particular problem, right? Both of the ones actually have more, especially this number b thing right here, right? Picture of a plus b plus a plus b. That's addition. This is not addition. This is multiplication, and it matters. I can do this for multiplication. That's why I get kind of like distributing exponents over the multiplication. You can't distribute exponents over addition. Okay? Now, there is one definition, and I do say it's a definition right now because we don't have a way of showing that it's actually true because we're not working in rational numbers, we're only working in whole numbers. But it's this idea that a to the 0 is 1. Anytime you're dealing with a power that's the 0 power, we're talking about a power of the value actually being 1. So what I want to do first, I want to show you why this works with some concrete sort of expressions, okay, with some numbers in there. So what you'll see on number 1 is you see 2 values, a, right, a and a, 2 bases, and they have different exponents. They could have the same exponent. But I have an example of property 1, right? Okay. Well, what does a cubed actually mean?
A times a times a.
Right? This is a cubed. What does a to the 4th be? How many a's are there? There are 7 A's here total. So this is A to the 7th, and why is it 7? Well, because this is actually 3 plus 4. Okay? So you can actually do it with these numbers. You can see it happen for you. It has to be addition of those. It's not 12 of them, right? I don't have 12 A's, I only have 7 A's. I can do the same kind of thing on number 2. So this should be subtraction, right? Oh, I didn't write this one in. So this should be subtraction, but a to the 4th, as you guys told me a moment ago, looks like this. And a cubed looks like this. So what would you do next if you were working this problem out? Yeah, you cancel them out. They actually divide out to the number 1, right? So these two divide to the number 1, these divide to 1, and these divide to 1, and I end up getting as a solution a to the 1. Well, where did that a to the 1 come from? It's 4 minus 3. I actually subtracted the 4 minus the 3. I've got a couple more. All right, so this is the one where I told you get to multiply. I'll show you why it works. Okay, so you already told me a minute ago what a cubed is. It's AAA, right? Yes. And then squared means I have this item times itself. Right? AAA times AAA, and how many A's do I have? 6. There are 6 of these guys. And that is because this is 2 times 3, or 3 times 2, or whatever. Cool. All right, one more. Okay, so this is the property that we learned on the last 2 slides ago. AB to the 4th means I have AB times AB times AB times AB. Right? That's what the power of 4 means. Okay, and write it down times itself 4 times. Okie dokie. But I actually would rather much have the A's all together and then P's all grouped together. So what property allows me to do this? Not the distributive property. It is the commutative property. Distributive property is a property that applies to either multiplication over addition or multiplication or subtraction. And we actually saw very briefly at the end, if you watched to the end of the video that I recorded, it actually works for division as well. It's the only property that helps for division. But the idea of moving the objects around would be a commutative property. I actually kind of have some associative properties that are going on there too, right? Because I kind of removed those parentheses and I said we can reassociate as we remove things. There's kind of that going on too. Commutative property is the biggie. So how many A's do I have? 4. And B's? 4. So A to the 4th, B to the 4th. And again, this ability to be able to move them around, that's a commutative issue, right? Commutativity is the multiplication of all multiplications. That's why I don't have that property for the addition I remembered a little while ago. I don't have a commutative property that applies to multiplication and addition at the same time. Okay? That would be a distributive property. All right, so what we're going to do next is we're going to take a couple of examples. One is a little bit quicker and easier to do than the other. And which one of these is quicker and easier to do? A is. Why? What's nice about A? They're all the same basis, right? Okay. So looking at A, what am I going to do?
Just add 10.
Okay, I'm going to add the exponents, right? And so this is sort of just like an extension of property number 1. I've got 3 of these guys all from the same base, so I can add all of their exponents. So we have 5 to the 10 plus 2 plus 4, which is 5 to the 16th, and this is the expectation. You don't need to grab your calculator and tell it 5 to the 16th. If you do, I imagine it's going to turn things into scientific notation for you. And this is going to be a very large number. Okay? So this is where we would leave it. Okay, so what are we going to do with B?
We could change them all on the same base.
We could change them all on the same base. Do you have any ideas about how you might tackle doing that one?
Multiply. Good idea.
Eventually, say that louder, Kayla.
2 and 3 together.
Why would we want to do that? It would equal 6. Why else could we do that? Because the exponents are equal. You see that? They're both exponents of 3. What I'm actually going to do, I'm going to use property number 4 in reverse. So the 6 to the 4 gets rewritten. And I used property 4 backwards, didn't I? Does everybody see that? Because there are occasions where your book likes to ask you what property was used, don't they? Yeah. This is property 4. They took that number and they sort of undistributed the exponents. And that's exactly what we wanted, and Kayla's right, because we wanted them to have the same base. And 2 times 3 is 6. So now I have 6 to the 4th, and I have 6 to the 3rd, which means I have 6 to the, thank you, 7th. Anybody else think of something you could do differently? There's one other thing we could do in this problem. Okay, let me show you. You could split apart the 6. Yes, you could. So instead of combining the 2 and the 3, you could split apart the 6. So you could split this apart like this, and then reapply rule property 4, right, to each of these. This is 2 to the 4th times 3 to the 4th times 2 to the 3rd times 3 to the 3rd. Okay. Just depends on what you see in the problem, and this is actually a very valid thing to do. And there are situations where you do this in mathematics too, where you want to split apart rather than squish together. So then we can group the 2's together, right? So this would be 2 to the 7th, and then times 3 to the 7th. And this is every bit as much a simplified form as 6 to the 7th. Yes.
So when we have the same base, we don't have the exponent together.
When you have the same base, you do add the exponents together.
Like on the first example, like
Mm-hmm.
then 2 and 3.
Right here?
Yes.
Okay.
When you put them together, like 2 times 3, I feel like we're just supposed to add 3 plus 8 on that.
Oh, no, we're undistributing. Remember the property back on this slide, let me go back up to it. The property on this slide says that if I have a single M out here, it distributes to the A and it distributes to the B. So basically I have it on the A and the B. I'm basically starting on this side and I'm plucking the M out. It's kind of like I'm undistributing, or we call that factoring when we do multiplication. It isn't called factoring here, but sort of remove that piece of it like you're factoring it out. Yeah. Okay. Let's see what's next. We're going to do some multiplication algorithms, okay? All right, so the standard algorithm for multiplication, I'm going to do it with you first, and I'm going to show you how the expanded form of that looks. All right, so somebody's going to help me. In fact, does anybody want to come up to the board and do it? Caitlin, join me.
I'm always first one.
All right, Caitlin's going to multiply 48 times 32. You watch her because she needs some help if you need help.
Just regular?
Just regular, just
Okay.
doing standard multiplication.
Oh, that's really small. Whoa. Hold on. Did I do that right?
So far, so good.
Oh, okay.
Did we do 3 times 8? Did we ever do that part of it? No.
Yeah, that's what I was saying.
Oh, that's where you got stuck. That's okay.
Oh, I did it
was
wrong.
really
I
worried about
added
it.
instead of multiplied.
It's okay. Erase one line up. Smart works the fun in it. Okay.
You know.
All right, so try again. You got your 0 in the right spot.
4.
Yeah. That's okay. 1536. Everybody agree? Good. Thank you, Kate. All right, so this is the one that you guys are familiar with. You've done this for years. Since you're probably somewhere about like 9 years old. Probably a decade. That's probably about right then. Yeah, about a decade. We won't say how long I've done it for, but longer than a decade. All right, so most of you probably feel very comfortable and familiar and you like this method just fine. But I want you to take your hat off for a moment and think about, if you're seeing this for the first time, what are some of the things that could cause you concern or cause you to make errors in this method? The zero placeholder, where'd that come from? It's an awkward thing to do. Is what else? The carrying thing, right? You're carrying the multiplication, and in the middle of multiplying you add. That's a little awkward, right? You're in the middle of multiplying and you add something in the middle, and of course when you're done with all the multiplying, you get to add again. Okay? So the first thing I want to show you is the expanded form that explains this a little bit. Okay? All right, so 48 is actually 40 plus 8, right? I'm going to take that as a guess. Okay, good. And then 32 is 30 plus 2. Okay? What I'm going to do next is I'm going to write this as multiplication beside each other on the same line. Okay? So 40 plus 8, oops, that's not supposed to be there, times 30 plus 2. And that starts to look an awful lot like this problem on the board. I knew I left it up there for a reason. A plus B plus A plus B. Right? And the first thing we were asked to do when we did this on the board, I erased it already, it was over here, was we were asked to do it using the distributive property. Do you remember that? I want to do this problem with that distributive property for a moment. So we're going to take this first value and we're going to distribute it to each of these. So this is 40. I said it was 40. Let's try again. Make it 40. This is 40. How did I do that? Okay. All right, 40 plus 8 times 30 plus 40 plus 8 times 2. Right? And then we're going to do a distributive property again, yeah? Okay, so this is 40 times 30. Just bear with me. This is not an actual algorithm. I want to show you where things are coming from, though. It's important. 8 times 30 plus, this is 40 times 2, plus 8 times 2.
Can't you skip that?
What do you want me to skip?
Can you just do like 40 without like doing I can choose. Never mind.
Okay. That's okay. I'm going to show you cooler methods than this in a second here. What is 40 times 30? What is it?
1,000.
1,200.
Teamwork, yes.
4 times 3 is 12, right?
Yes.
And you got the 0 and the 0 there. There's 2 zeros, yeah? All right, so we got 1,200. How about 8 times 30? 240. 40 times 2? 80. 8 times 2? 16. All right, so let's imagine putting these, we'll line them all up. This is 1,200, 240, 80, and 16. So we'll do our standard algorithms we did before. In fact, we'll do scratch addition. How's that sound? 0, 0, 0, 6 is, hey, come now. All right, 0 plus 4 is, plus 8 is 12. So we scratch and we keep the 2. 2 plus 1 is 3. I scratched how many times? 1. You guys act like this is horrible. You're doing this fine. 1 plus 2 plus 2?
5.
It's 5. There's 1536. Okay, so the standard algorithm is actually a distributive process all in condensed form. Okay? Well, I didn't say this was a method. In fact, we're going to get to something that's going to make this look a lot better. Okay, so watch this. This method is called partial products. This partial products method is going to look a lot like part B that's on the board. And here's how it works. We already established on the board before that this is 40 plus 8, right? And then this is 30 plus 2. Agreed? We're going to draw a rectangular area diagram. And our diagram does not need to be drawn at all to scale. It just needs to have 4 quadrants. Okay? 40 and 8 either go on the top or on the sides. This is 48 because that's 48. This is 30 and 2 because this is 32. Everybody with me? Yes. Each little corner is actually the product now. Okay? So this top left-hand quadrant here is actually 40 times 30 because that's the two that are going to be sort of lining up in it. So 40 times 30 we did a minute ago. Do you remember what it is? Okay, good. 1,200. How about 30 times 8? 240. 40 times 2? 80. And 2 times 8? 16. And then we have 1,200, 240, 80, 16. We end up 1536, just like we did a minute ago. But there's a lot less work we're showing now. Partial products is wonderful because it solves 2 problems that you just identified a moment ago that can be tricky when you're learning the standard algorithm. Number 1, it solves the issue of multiplying and adding at the same time. Right? All I did in the middle of my diagram is multiply. All I did when I'm done was add. There's no mixing up those 2 operations. The other thing that it does is it very clearly shows you where all those zeros came from, doesn't it? So when we did the standard algorithm, and I didn't do it because I had Caitlin up here doing it, and we had this issue of where did the 0 come from? Okay, there's a bug up there. All right, so we had this is 16 and 96, and then Caitlin had to put a 0 in here. So let's talk for a moment because you are going to at some point teach us standard algorithms. Why is there a 0 here? You're multiplying it by 30. Right here, when you do this multiplication is actually 2 times 48. This multiplication is 30 times 48. The 0 is there because you're not multiplying by 3. You're multiplying by 30. And when you multiply by 30, you've got a multiple of 10 in there, which is what Kayla was pointing out. So that 0 has to hold the place of that for that reason. But that's sort of lost in the middle of explaining that most of the time, and it looks a little bit like magic, right?
Yes.
We just put it there because it has to be there, otherwise the answers will be wrong. Okay? I really like partial products. I'm a big fan of this because I think the picture is awesome, and so many of our students are visual learners, and this has that visual component to it too, as well as separating out the different operations. So, all right, that's actually all but one of our methods for algorithms. Let's do this one real quick because we have just 2 minutes left, and that's all it's going to take. We've seen lattice multiplication before. If you've taken contemporary math, you've seen it in there. We've seen lattice addition in here, right? And this is very similar to both of those. We've got 48 times 30. We actually make a gridded box just like on the partial products. And instead of writing 40 and 8, we actually just write the single digits, 4, 8, and 3, 2. And notice it's on the top and the right. That matters. Okay? That's to the top and the right. We take our boxes and we split them diagonally, which you guys have seen before when we did lattice addition, right? And we multiply now instead of adding because we're doing multiplication. So let me start at the top left-hand corner. This is 4 times 3, which is 12. So we do a 1 on top and a 2 on bottom. 8 times 3, the 2 on top, 4 on bottom. 4 times 2, 8, so we put the 8 on bottom, and then I have 8 times 2, 16. And then I draw my diagonals in, and I change my color just to emphasize here what's going on. You see, what happened was whenever you multiplied a 2-digit number, you actually were able to put it in the column with its placeholder. That's what lattice multiplication does for you. You start in the bottom right-hand corner with a number 6, and then we're actually going to have to add. 4 plus 1 plus 8 is 13. A 3 goes in the bottom. I was getting ahead.
And what are we going to carry?
A 1.
A 1.
Okay. Okay, so don't get confused with the 4, the 8, the 3, the 2. None of these get added in here, okay? It's only the numbers inside the box. So now I've got the 1 that I carried, this 2, and this 2 for a grand total of 5, and then the top diagonal has a 1 for 1536. Things are a little bit more hidden here, but you still have the property that it separates the operations, right? All the multiplication first, all the addition second, which is nice. All right.